Hi folks, so today we're going to continue with our Understanding the Axial Stress series. So today we're looking at chapter 7, which focuses on the factor of safety, or safety factor as I like to call it. So we're just going to have like a very quick summary in terms of the content covered thus far. So we started off with an introduction into material failure. So we touched on things like creep, fatigue, ductile and brittle failure. And we proceeded to look at what constitutes stress and strain. So we stated that stress is basically the measure of the amount of pressure that a component is being subjected to, which will lead to eventual deformation. So whether that is elastic or plastic, or eventual rupture, that essentially quantifies what stress is. And that measure of deformation experienced by a component or engineering material, that's what we define as strain. Moving on from there, we looked at what is the Young's modulus. So the Young's modulus characterizes a material's resilience against deformation. And we also looked at what is that measure of energy that causes deformation in material, which is basically the shear energy. From there, we looked at thermal load. So other than having an applied force or load to cause deformation in material, essentially any form of external stimulus can cause deformation within material by increasing the levels of stress within the component. So this is where we looked at temperature differentials and how those temperature differentials impact in terms of how materials eventually deform. From there, we also looked at the concept of compactability. So if we have a situation whereby there is a measure of indeterminacy in a component due to sections of it constituted of different materials, or whether there is a change in the cross-sectional profile, then we can use these concepts to figure out what the measure of stress and strain is within the component. And the last chapter that we looked at, which was chapter 6, had to do with shear stress, the concept of shear stress. So shear stress, just to quickly summarize, is if we have a situation whereby the load acts on the component, though in plane, is offset to this neutral axis of the component in a manner that causes the component to distort and eventually shear along the what I call the axis of shear. So that's basically the neutral axis. Then that's basically shear stress. So hopefully you've watched these videos leading to this particular one. So we're now going to be looking at what is the factor of safety and why is it important when it comes to designing engineering components. When it comes to the design and manufacturing of engineering components, there's always that measure of uncertainty that's not necessarily factored when it comes to design. For instance, if a product is fabricated or machined to yield a particular form or shape or a desired component, there's a good likelihood that the material could have manufacturing defects. So whether it's through casting, machining, forging, whatnot, or even molding, so let's devoid of what the material is. There's always that possibility of microscopic defects within the material, probably due to the quality of the material pre-manufacture, or surface defects on the external surface of the material, which could constitute what's called stress risers. And these stress risers more or less amplifies the level of stress within those regions where there's that presence of microscopic or macroscopic defects. So this is where the factor of safety comes into play to ensure that at least the component or the material is safeguarded to operate within the elastic limits of a given component, unless it's intentionally designed in such a way that it does need to experience some measure of plastic deformation. Now, the other uncertainties that also need to be factored into place. So if we're looking at uncertainty in terms of the operational environment of the component, the nature of the media that the component is likely to engage in, which is where it hasn't been encountered in terms of the design consideration of the product. All that needs to be looked into in terms of what will be the ideal measure of the safety factor to ensure that the material is operating in an environment whereby the likelihood of possible failure has been accounted for. We can also look at the loading conditions, so in terms of the nature to dynamic loading on the component. Is the nature of the dynamic loading such that it's likely to amplify the measure of stress on the component, which could lead to the component failing as a result of fatigue or creep. So these are some of the things that needs to be considered from a designer's perspective. So how can we go about defining what the factor of safety is? So I've defined the factor of safety as follows. The factor of safety, or the safety factor, so in some books, the safety factor is denoted by the letter small n. Some people like to use FOS, but I prefer using small s subscript f. So this is basically some form of index that defines a certainty of permissible strength capacity of a design component within the deformation limits of a given material. So that's essentially how I've gone about defining what the factor of safety is. And this can be determined mathematically as follows. So the safety factor, that particular number, that particular value that we're looking at, is basically the ratio of the failure limit, or the failure stress, to the design stress, or the allowable stress, or the working stress. And we can also relate this to shear stress conditions. So the safety factor, if we're looking at component being subjected to shear forces and shear stresses and things like that, then we can look at the shear limit, or the shear fail limit, to the allowable design limit in terms of shearing on the component. So if you have a situation whereby the safety factor is equal to 1, then you're more or less looking, at a situation whereby the design limit is more or less equal to the failure limit. So whether the failure limit is at yield or at UTS, that's essentially what's being defined. And considering the fact that we've talked about these uncertainties, it's not really a smart thing as a designer to do to design your component to yield unless it's done intentionally. So ideally, you want this value to be greater than 1. So you're looking at the design stress, or the working stress, to be considerably smaller in comparison to the fail limit of that given component in respect to the material that's been fabricated from. So as I more or less pointed out, what constitutes the variables within the formula and working out the safety factor. So sigma I is basically the defined stress failure limit. So that could be the yield limit, that could be UTS. So again, it's more or less down to the designer's understanding of that material that they want to more or less realize a particular component from. And sigma D is basically the design limit, or the allowable or operational stress that you want the material to measure to in terms of the measure of stress due to loading conditions. All right. And likewise, tau I is the shear stress failure limit. So whether that is to respect to the UTS of the material, or if that's respect to the yield limit of the material, then essentially that's basically the shear limit. And tau D is more or less the design shear stress. Okay, so in terms of the relationship of the shear failure limit to the stress failure limit, it's normally between 0.05 to 0.5 of the yield limit of a given component, or whatever that stress limit is in terms of what the shear equivalent will be. And this is all dependent on the material. So the brittle the material, the more likely the ratio, the smaller the ratio is likely to be. And the more ductile the material, the more larger this value is likely to be. But again, it all comes down to your knowledge of the material that you're actually considering in the design and development of a given component. So let's put this in a bit more context. So again, we're revisiting the characteristic curve of a typical material being subjected to a tensile test. So as we looked at a couple of chapters ago, if we can put in that context, there are two regions, well, essentially three regions in terms of how a material more or less deforms. So you've got the elastic region, whereby once you more or less remove the stresses, well, not necessarily the stress, because residual stresses are very difficult to remove, but let's say if the external stimulus is removed, so if we're looking at forces acting on the component, once that's removed, the material is able to come back to its original state in terms of its original length, or whatever the initial state of the material was. Then once the material goes beyond the yield limit, between the yield limit and the ultimate tensile strength of the material, this is where the material starts to deform plastically, but it deforms in a much more uniformed manner. And again, this is where the material is also experiencing some measure of what's called work hardening. Okay, so we'll talk about the concept of work hardening down the line. Then after the UTS limit, this is where the material then starts to accelerate rapidly towards the rupture stress, whereby it eventually fails. And this is where it's a bit non-uniform. So again, you're not having any increase in the stress in the material, you're more or less having like a fall. So there's a drop in stress, but there's an increased rate in terms of the strain, which will lead to the eventual rupture of the material. So in terms of from a designer's perspective, what you really want to do is you want to ensure that, devoid of these uncertainties, the material, okay, is more or less deformable within its elastic region. And this is where this diagram comes into play. So the closer the value, or the smaller the value is to 1, the closer it is to the yield limit. So again, you need to have a very good understanding in terms of why you're choosing a particular factor to define what the design or the allowable stress is for your given component. So in the red region, you're more or less looking at materials that you have a very good idea or a very good or substantial knowledge base of the material. And you're also looking at situations whereby loading is not critical. And again, anything from 1.5 to 4 and above that, this is where you're looking at situations whereby the knowledge base is not that great. There's that possibility of new materials that you don't really have enough substantial data in terms of how that material would behave and how much it can realistically endure in terms of eventual failure. Again, having some uncertainty in terms of the quality of the material and things like that. But there's one thing that needs to be understood here, that the greater the safety factor, the more likely your component or product is more or less going to be overly engineered. And if it's overly engineered, that means that it contains too much mass, thus it becomes quite heavy. So the whole objective in terms of designing, other than designing a component to ensure that it doesn't fail during service immediately, is to also ensure that you've got that balance between strength and material right, because there's also a sustainability element to that. But again, that's a discussion from another time. All right, folks, so hopefully everything made sense to you. So any comments that you have, can you just type it down below? And hopefully you join me in the next session. So please share and subscribe, and I'll catch you in the next section. Bye for now.